Hey everybody, welcome back to Mr. Murray's Mathland. Mr. Murray here, and today we're taking a look at another classic free response topic, and that would be differential equations and associated with that slope fields. Of the 6 free response questions on the AP exam, one of them is almost always guaranteed to be a differential equation problem. And sometimes it has a slope field component to it. So I threw this in here because slope fields should really not scare anybody off. They're a piece of cake. So here we go. Number 1, consider the differential equation given here, dy dx equals 2x over y. And sometimes you have to draw your own slope field at a small number of points. And lately they've been doing more of this. They're showing you the slope field right here for that differential equation. And on this slope field, they want you to sketch the solution curve that passes through the point 1, negative 2. And notice that point has been highlighted for you. So if you are a little confused about what a slope field even shows you, just remember that the differential equation, aka the derivative of the sort of solution, the original function, if you will, gives you the slope at that point. So at 1, negative 2, notice if you were to plug that in, 1 for x and negative 2 for y, you would get 2 divided by negative 2, which would give you negative 1. So notice at that point, it's showing you, at least with a nearby slope, that has a slope of negative 1, the graph would at that point. And so the slope field is showing you all the little mini tangent lines, with their corresponding slopes at different points on different solution curves for the entire set of solutions to this. When you integrate and you have plus c, this represents all of them. Depending on what c is, it would make it pass through a different point, and it might have a different shape. So we are sketching this one that passes through this point. And so to do that, there's some leeway given, but you start at that point, of course, and use the slope around it to basically give you the direction and the shape of the curve. And then you just continue on. Okay, the curve needs to be continuous, so you follow the slopes, and they seem to be heading down in this direction, and so I'll just do that to the edge of the graph. Now to the left here, there's nothing that would indicate there's an end to the graph yet. So you continue on, and you'll see it starts to flatten out. So you just try to mirror that with your curve, and then it starts to turn around, and there we go. That would be the solution curve for that particular solution that passed through that point. And there we go. So now we're going to move on and do a few other sort of common things. So part B here says, same differential equation, let y equals f of x be the particular solution that satisfies this initial condition of negative 2, 1. Write an equation for the line tangent to f at x equals negative 2. And use your equation to approximate f of negative 1.5. So this is a common thing, very easy, but there's a lot going on, so just make sure you're reading the question and answering it fully. So, this condition is really just telling you, hey, it passes through the point negative 2, 1. And we're going to write an equation for the line tangent to f at this point, at x equals negative 2. So remember, you need 2 things to write the equation of a tangent line. You need the point, and you need the slope. Well, I have the point. They've given that to me. That's the condition. And the slope, of course, comes from the derivative, or the differential equation, at this point. So I'm going to plug this point into my dy dx. And so 2 goes in for x, so that would be negative 4 on top over y, which is 1. So we have a slope of negative 4. So my tangent line is y minus 1 equals the slope of negative 4 times x plus 2. Okay, so there's my tangent line. And now I want to use that equation of the tangent line to approximate f of negative 1.5. So remember, this is a fairly common thing they have you do with tangent lines. It's called linearization. So I'm going to take my tangent line and I'm going to isolate y. I'm going to get it ready to basically plug in by just adding 1. So now y is isolated. And now f of negative 1.5 is going to be approximately what I get by plugging negative 1.5 into this equation for x. And remember, it's only an approximation because this is the equation of the line, and I'm using it to get the value of the curve. So it's very close to the point of tangency, so it's going to have a fairly similar value, but it's only an approximation. So then we simplify from there, and although if you were on a free response, you do not have to simplify, but negative 1.5 plus 2 is 0.5, and then negative 4 times a half is negative 2, and negative 2 plus 1 is negative 1. So f of negative 1.5 is approximately negative 1. And there we go. So we've written the tangent line, we used it to approximate. And part C. Now part C is not always a given that it's a follow-up to this sort of thing, but it sometimes is. We're going to find the value of the second derivative at this same point, negative 2, 1, that we used to write the tangent line. And then we're going to use this value to judge whether our answer in part B, this approximation here that I got, is that an over or underestimate of the true value of f of negative 1.5. So let's start with our differential equation, our derivative. It was 2x over y. And I'm going to find the second derivative by taking the derivative of it. And that's going to require a little quotient rule. So again, it's a simple one, so you might just be able to do it in your head. Maybe you're using a little chart, maybe you're using the low d high minus high d low rule. But remember, when you're doing this, it may require implicit differentiation, which is what we got going on right here. When I take the derivative of y, that is dy dx. So our second derivative is the denominator squared. So that becomes y squared in the denominator, and the numerator is the inners minus the outers, or low d high minus high d low. And if they were asking you to find the second derivative in terms of x and y, remember this is where you could take dy dx and replace it with this equation and do a bunch of simplification. But if you notice, it just said find the value of the second derivative at this point. So I'm not going to waste a whole lot of time, playing around with algebraic values. I'm going to get right to it and plug this point in. So 2 goes in for y, minus 2 times x is negative 2. And now dy dx, if you haven't actually replace dy dx with its equation, you need to get the value of dy dx at this same point, which if you've kind of stayed organized, we already did this in part B, and that's negative 4. Otherwise, you just go get it again. It's not, it doesn't take super long here, but that value right there of dy dx is negative 4 at this point of negative 2, 1. And then we are dividing by y squared, and the y value is 1, so 1 squared is just 1. So again, on an actual free response, you do not need to simplify, but this would be 2, negative 2 times negative 2 is positive 4, times negative 4 is negative 16, and that would be negative 14. And so there is our value of the second derivative at that point. And now what does that tell you about a tangent line estimation? And, always want to justify and do a little explanation as to why you're saying what you're saying. And so keep in mind, the second derivative tells you about concavity of the original. And so if I have a negative second derivative, that means you are concave down. So something like this. And remember, when you're concave down, no matter where you write a tangent line, you're going to be above the curve. So any estimate you get from that line is going to be above the curve's actual value. So you want to just say something to that effect. So let's see, since d squared y or dx squared is less than 0, the graph of f is concave down, and therefore the tangent approximation, and I'm just trying to word it in terms of how they asked it. They wanted to know, is your answer an over or underestimate of the actual value? So the tangent approximation is an overestimate, right? We're over the curve is an overestimate of the actual f of negative 1.5. Okay, so, you know, that right there is a big chunk of work. And as I've done on these review videos, I've intentionally made it a little bit longer than a real free response because they don't always ask the same exact thing. So I brought in a few of the most popular things, and that is certainly, you know, one of them. So let's take a look at the last part. And this is sure to be, for just about any differential equation, probably one of the, you know, 2 or 3 parts of it is actually finding the particular solution. It's not, you know, 100% guaranteed, nothing's guaranteed, but this is definitely, you know, as close as you can make a guarantee. Finding the particular solution. So that means finding the actual equation for the original function y equals f of x, which satisfies this given condition. So remember, when your derivative has both variables in it, you got to remember to separate your variables and get your y's with your dy, your x with your dx, or whatever variables you might be using. And so I'm just using a little algebra here. I'm going to multiply both sides by y to bring that over there, multiply by dx to bring that over there, and now I have y dy equals 2x dx. And so now I'm going to integrate each side. Now I've correctly separated the variables, and they're always very big, the graders on that if you don't separate the variables, you get 0 credit for this part. And this is usually like a 4-point, you know, component, like a biggie. So even that first step might get you 1 point. So now integrating, just using any kind of power rule. Sometimes you have to use ln, square roots, whatever it may be. But in this case, this is kind of a classic 1/2 y squared is equal to, over here, x squared divided by 2, you know, cancels that 2. And don't forget to have a plus c on at least one side. I mean, really just one side to represent the collection of all the constants. And now you're getting into the point where you got to do 2 things. You've got to plug in this point of 1, -3 to find c. And you also have to answer as y equals. You know, y has to be isolated and it has to be a function. So you've got to do some isolation for y, and you've got to find c using this point. It really doesn't matter where you do it, and every differential equation can be a little different. Sometimes it jumps out at you to do one versus the other first, and, you know, it's not that you have to do the same thing every time. I'm going to first get rid of this 1/2. I'm going to multiply both sides by 2. And so I'll have 2x squared, and I'm still just going to call this plus c, even though that's now going to be a different c than it was in the previous step, but it's still just a constant. And I don't know, this seems like a pretty good spot to plug in, you know, this point of 1, -3, now that there's no fractions or anything. So plugging in -3 for y and squaring is going to give you 9 there. Plugging in 1 for x is going to give you 1 squared is 1 times 2 is 2 plus c, and so c is 7 in this case. And just be careful where whatever you find for c, make sure you use it at the spot where you plugged in. So I couldn't go back and plug it in here, for example, because that's not the version of this equation I used. I used this. So that's the c that I just found. So here's where I'm at right now. Y squared is 2x squared plus 7. And we're not done again until you have isolated y. Your answer must be a continuous differentiable function. So I need to take the square root of both sides, plus or minus the square root. Don't forget that plus or minus because it's frequently important, and that would not be an acceptable final answer because plus or minus is not a function, that's really two functions, and you have to choose which one is appropriate here. And that just comes down to what was the initial condition they gave you. The initial condition was 1, -3. Your y value is negative when you plug in 1. So the only way to get a negative y value from this equation is to have a negative out in front of that square root. So this is where you have to know to sort of reject the positive and take the negative. If that y value had been positive, then I would use the positive square root. But they frequently in these will give you a negative y value. Not always, but they frequently will give you a negative to see who remembered to use plus or minus so that you actually remembered to use the negative. If they gave you a positive and you just forgot to do plus or minus, you'd get the right answer by just dumb luck. So, just be on the extra high alert there. And there we go. There is our particular solution. You can check if you like by plugging in 1 and making sure you do get out -3 for y. That's not a bad way to check if you have time. But we just ran through a lot of the major ideas that come along with a differential equation on a free response question. So hopefully you feel good about those things because it's almost guaranteed to be there year in and year out. If you have any questions, of course, please let me know. And if you'd like to see more examples of differential equations, check the AP website. And they've got tons of them there. And you can see all the little variations and different quirks they throw in there. All right, kids, let me know if you have any other questions. And as always, keep working hard.